Hi, so we're going to be talking about heap sort. First up, we're going to talk about how it works. So in an assignment from a couple weeks ago, you were actually asked to implement heap sort, and that's with the help of a min heap. Right? So the basic idea of a heap sort, you should be very familiar with it, is that given a list of random data, the first thing we do is to just heapify the input, right, using kind of a systematic percolate down so that it becomes a min heap. And then the second thing is then we just extract the minimum from the min heap iteratively, so that when we do that, they basically come out sorted. So, and if you remember from the assignment that you were asked to return a sorted shallow copy of the original list. You're not asked to um, sort the input in place. However, most of the sorting functions that we've studied so far, they sort in place, and so did the original heap sort. So, in order to kind of sort in place, we can make a very simple modification so that it appears to be sorted in place. So I actually typed it up here. So you should be, again, very familiar with this. You first kind of just build an input, build a min heap with the input, and then we create a copy uh, into which we'll extract all the mints and append them in the order that they're extracted into the output. Now, we do that in the loop, and when we run into the index error, that means the min heap is empty and we are done, right? And in order to kind of update the input in place, we basically use the list slicing, and we say we update the entire list with whatever's in our sorted output. All right, so now we have an implementation. We should test it. You should be very familiar with how to do this right now, so I'm not going to go into the details of this. So let's move on. So even though we did kind of appear to satisfy the requirement of sorting in place, there is a problem though, because doing the heap sort this way does use an explicit min heap, which takes up memory. This out thing is not free. Right? We basically copy the entire original list into the output. So in if the input is very large, has millions of items, that can be very slow. Or if you work in an environment in which memory is limited, that can also be a problem. So we want to write a heap sort that sorts truly in place with only an implicit heap, right? Not with an explicit heap. And with an implicit heap, what that means is that we'll just use the idea of a heap, but we don't explicitly build a heap. So before we actually dive into the details, I think it's good for you to kind of think about, in order to accomplish to do strictly or truly in place heap sort, what kind of changes do we have to make um, in order to accomplish that. So think about that for a moment. So there are two major changes we have to make to the heap sort using explicit min heap. So the first thing is, remember, in our min heap we don't use the first element in the heap, right? We say the first element starts at index 1 instead of 0. However, if we have to do this in place of the original input, then we cannot just arbitrarily prepend a slot in front of it. So we have to now work with a kind of a quote unquote min heap where the first element is at index 0. So what that means in terms of code, or in terms of looking for the children of a given node, is, so you can kind of see, right? Let's say, for example, the element at index 1, the two children of it is at index 3 and 4, right? The element at index 2, the two children of it is at index 5 and 6. So now take a look at, let's say if we for the element in index 6, where are its children and what are the indexes? And then kind of, I hope, after looking at a few of these, you can figure out a formula for just any element at index k, where is left child and where is right child. Okay, and the answer is, hopefully you see this, for 6, the true children are 13 and 14. So in general, for an element at index k, the left child is at 2k plus 1 and the right child is at 2k plus 2. Okay, so the second major change we have to do has to do with the fact that when we extract the minimums and we extract them in a loop, right? So we have a bunch of these sorted minimums. Where can we put them? We said we cannot use extra memory. Okay, so that could be a problem. Now, as it turns out, it could be pretty straightforward, because when we extract the minimum, the heap itself actually shrinks by 1. So the input now actually has a little empty slot at the end of the last position. So we can take the extracted minimum and put it there. And then when we extract the next minimum, the input or the heap again shrinks by 1, and we can put the second minimum in that position. So so that's actually pretty nice. So let's look at a very concrete example. So the this is a small little heap. So, and it's already being heapified, and now we extract the minimum, which is 1. Okay, and when we extract the minimum, if you remember, in the remove function, we take the last element and put it in at the first position. And then we just said we can take the minimum and put it at the last position. So effectively, we're kind of doing a swap. Okay, and now that the minimum's at the end, the heap becomes this smaller list. It's not truly a heap now, because we have the a larger element as the first position. And then we can do a little heapify or percolate down the thing we just moved up to the right place, and then to turn it back into a heap. So now we have a heap with a minimum or a sorted part at the end of the list. And then we can do that again. And now we will extract the second minimum, which is 3, and swap it with the last element. So 3 comes to the last element, and 12 becomes the first element. And then now we have kind of a heap that is not truly a heap. And then again, we do the percolate down of 12. And then now we have a smaller heap again, and we have a sorted list at the end of the input. Okay, hopefully that's clear how it works. And now it's your turn. So can you try to just complete the rest of the heap sort using the steps we just described? All right, and assuming that you've done that, I'm just showing the very last step here. In this very last step, this heap with 2 elements, we swap them, and then the heap becomes a single element, and we really don't need to do a heapify anymore with a single element. So anyway, so now we have a sorted list. Well, actually, so the entire input has been sorted. But one thing you kind of notice is that it's sorted in a descending order. We typically want to sort in the ascending order, so it's kind of reversed. So we can, as a last step, just reverse it. Or if we don't want to reverse it, there's actually a better idea, is that instead of using the idea of a min heap all the way through, we can actually use the idea of a max heap, so that when we're done, it's already in the right order. And the idea of using a max heap versus a min heap is actually pretty straightforward, and that is when we're doing any sort of data comparison, instead of using a less than, we just use the greater than.